Okay, good morning. What's up, everybody? Let's get into it. So today we're getting into chapter 3. We're talking about the vector space of linear maps. So this is a pretty important concept. One of the nicest facts about vector spaces is that if you look at ways to map one vector space to another, and you take all of those different ways, if you restrict yourself to the class of those mappings that respect the properties of the vector space, that is, like, preserve its addition and scalar multiplication, essentially, then you get back a vector space. That's the short story of it. So we'll start to get into this, but this is actually a really cool little trick. Basically, it says that if you're studying vector spaces, by looking at how you can map one to another, which is going to be one of the fundamental themes of how we'll try to understand vector spaces. That's been what we've done so far. We've asked ourselves, hey, how can I find little vector spaces inside of big ones, and so on? How can I put them together to make new vector spaces? How can I build a vector space out of the smallest vector spaces inside of it? That was the idea of a basis. All of these things are ways to map one vector space to another. Little pieces into a big thing into little pieces. This tells us what a vector space is like. Looking at maps between things tells us something about those things. The really cool thing for vector spaces, like one of the nicest pieces about it, is that these things, these maps that respect the properties of the vector space, form a vector space themselves. It's kind of a really it's not too complicated of a thing once we actually get into it, but if you think about it on a high level, it's kind of a cool, snake eating its own tail, strange self-referential thing. It feels kind of neat. So let's start talking about it. Here's the idea. A linear map from a vector space V to a vector space W is any function that sends V to W and has the following properties. The first off is additivity. This says that if you map U plus V, two vectors in V, the sum of them, what you get back is you get back the sum of TU and TV. That is, you can distribute T over addition. Here's an important thing to notice here. These guys are different pluses. This one is W's plus. This one is V's plus. That is, here, U plus V, that addition is going on inside of V. TU plus TV, well, T sends things from V to things in W. These are two things in W being added together. So these are using two different additions. So that's the idea. The addition in V gets essentially mapped to an addition in W. Similarly, there's a property called homogeneity, which says that if you map lambda V, what you get back is lambda times the mapping of V for all lambda in the field and all V in V. So the idea here, similarly, is that, well, I guess maybe I pointed at the wrong thing right there, that these here are different scalings. One of them is the scaling in V. One of them is the scaling in W. Notice an important thing right here is that the big piece here that is maybe kind of being hidden from you is that these things here are vector spaces over the same field. Or at least that's how we'll start thinking about it. You could potentially come up with an analog to this, where maybe one of them is a vector space over a field that is contained in the other one. But for now, let's just consider this simple case, since we want to do it in terms of this definition for all lambda in the field, and we're not specifying which field. If they are the same field, then we don't have to. Okay, cool. So linear maps just take an addition in V and map it to an addition in W. Take a scaling in V and map it to a scaling in W. Nice. They respect the two fundamental operations of a vector space. We'll use a little bit of notation here to represent the set of all linear maps from V to W. So the set of all these linear maps we'll denote by a cool calligraphic L and then V comma W. And then in the case where V and W are equal, we won't write V twice. Instead, we'll just write LV. So let's look at a few examples. Let's see. Okay, first example. Let's let T of V equal 0 for all V, i.e. T is the 0 map, which is usually also denoted by 0. Okay, is this a linear map? Then notice T of V plus W, well, if it sends everything to 0, well, then this is still 0, but that's the same as T of V plus, or here, I'll even put this a little bit more explicitly. Sends it to 0, well, that's the same as 0 plus 0, which is the same as T of V plus T of W, since both of those are also 0. Similarly, T of lambda V, well, since lambda V is just some other vector and a T sends everything to 0, this is still 0, which is lambda times 0, the 0 vector, which is lambda times T of V, since T of V is also always 0. Oh, okay, cool. So the 0 map is a linear map. Here I am maybe being a bit pithy. So here, you could take T from a vector space V to a vector space W, any vector space V, any vector space W. And here I'm saying for all V and V. And this 0 here is the 0 in W, just to be clear. But yeah, so the linear, so the 0 map is a linear map. What other things are linear maps? Let's take the map I that sends a vector space V to a vector space W. Let's define this by I, even easier. How about this? Actually, sorry, I've maybe made myself a little bit of an untenable position right there. Here's what I want to say. Let's take it from V to V. Let's have this guy be defined by I of little v is little v for every v in V. Okay. Then T of V plus W, well, that's just V plus W, which is by definition, or sorry, I of V plus W is V plus W, which is, well, I of V plus I of W, and I of lambda V is just lambda V, which is lambda scaling I of V. So this map, which is called the identity map, is linear too. Okay, cool. So the identity mapping from a vector space to itself is also a linear map. The 0 map from one vector space to another is also a linear map. What other things are linear maps? Here are a few examples. Now I will just maybe throw these out quickly so that we don't have to talk about it too long and you don't have to watch me write too much. But here's a few examples. If you want to see some more details on these ones, you can always check in your book where I think they spell it out a little bit more, or do them as exercises since it's kind of fun. Here's another one. So here, even define D, a linear map on the polynomials over a field by dp is equal to p prime, the derivative of p. Then, since the derivative is linear, so is d, i.e. the derivative, let me make that clear, that's a d and not a p, of p plus q. We all know derivative of a sum is the sum of the derivatives. I've written the q first for some reason. There we go. And d lambda p is lambda p prime, which is lambda dp. Okay, cool. So indeed, this part where I said that it's in the linear maps on the space of polynomials is indeed well justified by the linearity of the derivative. Integration also works. So for example, let's take T to be a linear map from the polynomials over, and maybe I should say here instead of polynomials over just a field, let's just say over R just to be easy. What is that notation I'm writing here? Okay, here, let me make that R. And let's take this to be the polynomials, make that a fancy looking P, over R to R, okay, by T of P is equal to the integral from, say, 0 to 1 of P of X dx. Then notice that T of P plus Q is equal to integral from 0 to 1 of P plus, or let me put my of x's just to be really clear, P of X plus Q of X dx, which is, as we all know, equal to the integral from 0 to 1 of P of X dx plus the integral from 0 to 1 of Q of X dx. And T of lambda P is equal to the integral from 0 to 1 of lambda P of X dx, which is equal to lambda times the integral from 0 to 1 of P of X dx. Really writing low on that page right there, but just to make it clear, this is also linear. I'm showing both of the properties. That is, this top one is T of P plus Q, or T of Q. And this bottom one right here is lambda T of P. So we've shown that T of P plus Q is T of P plus T of Q, and T of lambda P is lambda T of P. Linearity. Okay. Very cool. So differentiation, integration, identity maps, zero maps, there are plenty of others. Quite a few things turn out to be linear maps. There are also things that are not linear maps, but it is a far larger class of things than you may initially expect. All right, let's prove some facts about linear maps and see why we would even care about studying these things. Let's get into it. Okay, so here's the basic reason, probably the most foundational reason why we care about linear maps. We'll summarize this in a result known as the linear map lemma, which says the following. It says that if you've got a basis, v1 through vn, for a finite dimensional vector space V, here notice that this means V is finite dimensional, since we're assuming that it's got a basis. Okay. And you've got some other W1 through Wn in another vector space W, then there is a unique, this is important, linear map that sends V to W and satisfies T of Vk as Wk for each k from 1 to n. Okay, basically what this says is that if you've got a basis, then pick any elements that you want to map those basis elements to in another vector space, there is one and only one linear map that does that. This is kind of neat. Basically, what it says is that if you want to study how you can map one vector space to another, particularly for a finite dimensional vector space, if you want to study how you can map one finite dimensional vector space to another vector space, not necessarily finite dimensional, then all you really have to do is understand how you map basis elements. That is, since basis elements essentially define the smallest possible subspaces that a vector space is built up out of, that is the span of each individual basis element. If you take those spans and you take their direct sum, you get back V. That's what it means to be a basis. What this is saying is that break down a vector space into its littlest building blocks. Linear maps are entirely defined by how they act on the tiny building blocks. So that's pretty cool. You can really exactly understand how you can take the pieces of one vector space, the smallest pieces it's made of, that are also vector spaces, and send them into another that is entirely described by linear maps. So let's prove this. We want to build a linear map so that T of Vk is Wk for each k between 1 and n. We'll start by doing that. So let V be a finite dimensional vector space, and suppose V1 through Vn is a basis for V. Let W be a vector space, and let W1 through Wn be elements of W. Define T, a map from V to W, by T of V is equal to T of, well, since I can write every V in V as A1 V1 plus AN Vn, a linear combination of its basis elements right here, what we'll define it as is just this. This is possible since V1 through Vn is a basis, and therefore every V in V can be written uniquely as V equals A1 V1 plus dot 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 all the way down to AN Vn for some A1 through AN field elements. Okay. Taking what do we use? K as our index. AK equals 1 and AI equals 0 for I not equal to K, we get T of VK equals WK, right? So this T satisfies the property that we want it to have. To see that T is indeed a linear map from V to W, note that, well, let's write it out. T of little v plus little w, well, that's T of, let's write it out, A1 V1 plus dot 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 all the way down to AN Vn plus B1 V1 plus dot 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 Bn Vn. That is, I'll put this in a different color. This guy right here, this part is V, little v, and this part right here is little w. So this is just for some field elements A1 through AN and B1 through BN. They are unique for each choice of V and W. All right, cool. Put it together, we'll get T of, well, I'm going to do a lot of steps at once right here. A1 plus B1, V1 plus all the way down through AN plus BN, VN. Agree with that? Hopefully so. Basically, all I'm doing is using the commutativity of addition and the associativity, the distributivity of scalar multiplication over addition. All right, cool. Oh, and associativity, I suppose, just to get rid of some of these parentheses and so on. But okay, so once I'm here, notice just by the definition of T, it takes a linear combination of basis elements and maps it to a linear combination of the corresponding elements W1 through Wn in W. So this turns into A1 plus B1, W1, plus all the way down to AN plus BN, WN, which, if we start to break it up, is A1, W1, plus all the way down to AN, WN, plus B1, W1, plus all the way down to BN, WN. This is just repeating the step I did right up here in the first two equalities, just backwards now. And hey, wouldn't you know it, that is T of A1, V1, all the way down to T, or of AN, VN, plus T of B1, V1, plus all the way down to BN, VN. That's a V, a terrible V. Okay, cool. And just from up here, the part I wrote in pink, this is T of V plus T of W. Likewise, we have T of lambda V. Well, this is just T of lambda A1 V1 plus dot 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 all the way down to AN VN, which is just T of lambda A1 V1 plus all the way down to lambda AN VN. Okay. By the definition of T, this is lambda A1 W1 plus all the way down to lambda AN WN, which, if I just do a little bit of undoing what I did in the first step, is lambda A1 W1 plus all the way down to lambda, or sorry, take out the lambda. I'm taking out a lambda from everything, AN WN, which, wouldn't you know it, is lambda T of A1 V1 all the way down to AN VN, which is lambda T of V. Hey. So T is linear. Now, for uniqueness, all we have to do is show that if some other map satisfies this property right here, then it's the same map that we just constructed. So let's suppose that T prime, a linear map from V to W, satisfies T of VK is equal to WK. Then, T prime of VK is equal to WK. Then T prime of V is just equal to T prime of A1 V1 plus all the way down to AN Vn for some field elements, since you can write any V in the vector space as a linear combination of the basis elements. Okay, cool. And then by linearity, this just turns into A1 T prime of V1 plus all the way down to AN T prime of Vn. Maybe this is more clear if I put some parentheses, but I'm just splitting up across the sum, which I can do by linearity, and I'm pulling out scalars, which I can do by linearity. Okay, cool. And this is just A1 W1 plus dot 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 all the way down to AN WN. But hey, wouldn't you know? That is how we define T of V. right up here. Oh, hey, would you look at that? So t prime of v is t of v. For all v, since they agree at every little v and v. All right, cool. So if you have a linear map, if you have a basis for a finite dimensional vector space and some set of elements in any other vector space, there is one and only one linear map that sends a basis element to the corresponding other element that you've chosen in W. That is, a basis is an ordered collection of vectors that is linearly independent and spans V. Pick any other list of vectors in any other vector space W. Doesn't have to be finite dimensional. There is one and only one way to map the ith element of your basis to the ith element of that other list in a linear fashion. All right, let's see what we can do with this. Well, it turns out that we can do quite a lot with the linear map lemma, but before we start talking about exactly all of those things, it will be really helpful to have a little bit of additional language. That is, linear maps have some other properties that are very nice, and some that I've alluded to previously, and if we talk about those first, it'll make a lot more clear the consequences of the linear map lemma. So we're going to talk about some of the algebraic operations we can do on the set of linear maps from V to W. Right now it's just a set. We haven't yet shown that it's a vector space. It is, but let's talk about it. So this might remind you of a homework problem we did. What we're going to do is we're going to say, hey, suppose you've got two linear maps from V to W, and you've got some scalar. Okay, we'll define the sum of those two linear maps and the product, scalar times linear map, in the following ways. We'll take the sum of S and T to be the linear map that sends a vector V to S of V plus T of V. Then we'll take the scaling, lambda T, to be the linear map that sends a vector V to lambda times T of V. Okay, cool. Now, are these guys linear maps? We should indeed confirm it. It is a useful thing to do. I will spell it out really quickly over here. Notice S plus T of V plus W. Well, this is S of V plus W plus T of V plus W, which is S of V plus S of W plus T of V plus T of W, which if I just use the commutativity of addition a little bit, this is S of V plus T of V plus S of W plus T of W, which is just S plus T, that new map of V. That's a V, not a W. It's a V with a little serif, plus S plus T of W. So, look at that. If I map V plus W through S plus T, I get S plus T of V plus S plus T of W. So, it does indeed respect the addition. It is additive. You can do the exact same thing with scaling. It's not too bad. S plus T of lambda, or sorry, not S plus T, of lambda V here will be S of lambda V plus T of lambda V, which is lambda S of V plus lambda T of V, which is just lambda scaling S of V plus T of V by distributivity, which is just lambda of S plus T of V from the definition of S plus T. Oh, so it's homogeneous as well. The same justification works over here as well. I'll leave that as an exercise. So this is how we show linearity for that one. The other one, I will leave that as an exercise for you. All right, it's not too hard at all. But so yeah, you can take two linear maps, put them together, make another linear map. You can scale a linear map, get another linear map. Very cool. Accordingly, since we've already talked about how the 0 map is a linear map, this guy is a vector space. The proof is routine. And I will leave it as an exercise. You do it yourself. It's not too bad. I hope it is relatively obvious. We have essentially done this in the homeworks. So if you don't believe it, please just look back at homework 1 and think about what went on there. It shouldn't be too bad to see that I think, was it the last problem? It was the one where you were, or is it homework 2? I should look at the problems. Anyways, it's the one where you're dealing with the linear maps from a set S to a vector space V. You were defining an addition of, or defining a notion of addition and scalar multiplication to turn it into a vector space. This is essentially just a subcase of that. That is, the reasoning you did there is basically identical to what we just wrote up here for linearity. Same exact kind of thing over here, and the rest of the verification of the vector space properties is similarly routine. It is tedious to write out. I won't do it here, but if you don't believe it, you can do it really without any trouble. So, cool. There is an extra thing you can do with linear maps that is really cool. That is, you can do composition, which is essentially like a notion of multiplication, if you want to think about it like that. So if you take T to be a linear map from a vector space U to a vector space V, and S to be a linear map from V to a vector space W, then the product is a linear map from U to W, defined by ST of U is S of T of U. That is, you have U, and you're sending it over by T into V, and V, and you're sending it over by S into W. You can just whoop on over with ST. That sends U to W. Why do we write it as ST instead of TS? It's convention. If you look at it this way, it might seem easy to write it as TS, but if you're thinking about it compositionally, where you're plugging in something to S, notice you do T first and then you do S. So since we write composition as like T of something, S of something, in parentheses, this way, let's just do this. Otherwise, we'd have to have ST of U is T of S of U, which would seem sort of counterintuitive. And I think people make a lot more mistakes when they do that. So this is just the general idea. You can take linear maps with compatible domains and codomains and put them together so that you get a linear map that sort of jumps over the middle space, if you think about it like that. This is cool. This is not something that you automatically have just for some random vectors. In that sense, these are kind of distinguished vector spaces. They're vector spaces, but they have an additional kind of way to put pieces from different ones together. Very cool. So here's a few algebraic properties of linear maps. The proof here, I will also leave as an exercise because it is, again, routine. But we'll talk through them briefly at least. The first is that you have associativity. That is, if you take T1, T2, T3, product of all those guys, if you do the product of T1 and T2, and then take the result of that and multiply it by T3, it's the same as taking T1 and multiplying it by the result of the product of T2 times T3. So that is, it doesn't matter what order you do the multiplication of linear maps with compatible domains and codomains. That is, the products make sense. Okay. So if T mapped U to V and S mapped something else to W, then this wouldn't make sense, right? You couldn't draw this picture. So here you've got like U to V to W to like Y or something. Here you've got T1, T2, and T3. You need something that looks like this for this to make sense. Okay, so yeah, okay, cool, easy enough. Similarly, identity, if you take the identity map, then if you compose T with the identity, That's the same as the identity composed with t, which is still just t. But here's the important thing to note. The first I is the identity operator on v, and the second I, which I will put in a different color, is the identity operator on w. So one's on v, one's on w, which are different maps if v and w are different spaces. But ultimately, it's not too big of a deal. All right, cool enough. Finally, the distributive property. So if you take the sum of two linear maps that you can add together and you then multiply by t, then you can distribute this multiplication across the sum. This is a pretty interesting fact. That is, since you can put two linear maps on the same space together and add them up and get a new linear map, that's what we talked about up here. And since you can multiply linear maps with compatible domains and codomains, it is kind of crazy if you actually think about it at first, though it's not hard to show, that putting linear maps together is compatible with composition. So it says if you add S1 and S2, take that result, do T, and then do S1 plus S2, that result, to the result of doing T, then it is the same as the result of doing T, then S1, and T, then S2, adding those two maps together. Okay, so you can split up sums of linear maps across this composition, and you can do it on either side. It doesn't matter what side you do it on right there. Okay, cool. Nothing too crazy. Like I said, this is a really routine thing to verify. All you have to do is just punch through and use this definition right here, along with these basic properties, and you will get everything you want. All right, now that we've got some notation out of the way, let's get back to seeing what we can do. Okay, actually I lied. We're not going to talk about what we can do with the linear map lemma today. I was thinking ahead to the next section. Instead, we're just going to round it out with a real nice simple proof. Super quick, super fast, and then we'll be done for the day. So, here's the easy proof. Next time, we'll use all the power of the linear map lemma, and we will continue to use it many different times throughout the course of this class. But for now, let's just do a quick, easy proof and be done. This one doesn't even require anything particularly fancy. So just a good, basic result that we'll use to wrap up the day. And then next time, we'll deploy our big guns. So this time, what we're going to prove to end is that linear maps take the 0 vector in one space to the 0 vector in another vector space. So here is the thing that we're going to prove. We're going to say, hey, suppose T is a linear map from V to W. What we're going to say is that T of the additive identity in V is the additive identity of W. Okay, this makes some sense. Linear maps respect the vector space's operations, that is addition and scalar multiplication. They preserve them. They map one set of operations to the other, basically. It makes sense that it should preserve the additive identities as well, right? Basically, linear maps should preserve all of the vector spacey properties of vector spaces. So, suppose that T is a linear map from V to W. Then we have, I will write it this way, T of 0. Well, that's the same as T of 0 plus 0. Since 0 is the additive identity of V, okay, this is T of 0 plus T of 0. This is by linearity of T. Okay, cool. And I'll even put parentheses there. I have not been writing parentheses normally for linear maps, which is pretty common. All right. So I'll even keep this going right here. So I'll keep my T of 0s on either side. And what I will do is I will add a minus T of 0 to this. So minus t of 0 plus t of 0 plus t of 0. Okay. And now I have 0 over here. And this turns into, well, I will write it like this, 0 plus t of 0. Okay. We're going to add minus t of 0 by the existence of additive inverses in W. Okay, cool. This is just the definition of additive inverses. Maybe there's technically a small step right there where I am skipping, like regrouping my parentheses and using the associativity of addition. So I should say and associativity. Of addition in W. Okay. And then this last piece just gives us 0 is equal to t of 0. And this just comes from the definition of the additive identity. That is, if 0 is the additive identity, then do it to anything and you just get back the same thing. Okay, cool. We just showed that t of 0 is 0, and we justified every single line of this with kind of some overly robust detail. Nice. Next time, we'll do some cool stuff. We'll really get into it. See you then.